Every known physical phenomenon, atoms, light, and even forces, are the result of interactions between a handful of known particles. To describe their behavior, physicists have constructed the Standard Model of Particle Physics, a theory which has been evolving for the last century, yet which is still as mysterious as it is remarkable. Pushing the limits of our knowledge further, however, will require tools at the frontiers of scientific achievement. And new technologies, while developed for pure science, are bound to serve more immediate practical applications, such as improving nuclear energy infrastructure. Nuclear power can be controversial, but consider this. Contained in a single M&M-sized piece of uranium is enough energy to power your household for the next 25 years. That's part of why I'm working on nEXO, the next Enriched Xenon Observatory, an experimental detector that will explore some of the finer details of the Standard Model, but which could also lead to advances in technology for designing, monitoring, or securing nuclear power systems. nEXO will search for a rare nuclear process called neutrinoless double beta decay. Single beta decay is the transition of a neutron into a proton, where an electron, shown here in blue, and a minuscule particle called an antineutrino, shown here in green, are emitted. Neutrinoless double beta decay, on the other hand, takes place when an atom beta decays twice, simultaneously, with the antineutrinos colliding and annihilating. This is a possibility predicted by some physics models, but forbidden by others. A direct observation would indicate which theory is correct. The challenge? For one, this process can only occur for certain elements and isotopes. nEXO uses xenon. Second, it is so rare that for a given atom of xenon, you'd expect to wait more than 800 trillion times the estimated age of the universe before observing it. That's why nEXO uses 5 tons of liquid xenon to improve the chances for detection. And third, antineutrinos are unfathomably tiny. One could easily pass through a light year of solid lead, so nEXO measures the energy of everything but the antineutrinos. This then allows accurate inferences to be made about the antineutrino behavior. My job is to use supercomputers to simulate the detector before it is built, to minimize false positives that could bury the elusive signal. An ounce of prevention is worth a pound of cure, so modeling the detector before it is built will ensure that if nEXO detects neutrinoless double beta decay, we can be certain that we've not only found one of the rarest events to take place in the universe, but we will be one step closer to understanding the building blocks of our world.